Taylor and Maclaurin series. Taylor series centered at 0, also known as Maclaurin series. Let f of x be defined by a power series about 0 with a non-zero radius of convergence. That is, f of x equals c0 plus c1 times x plus c2 times x squared plus c3 times x cubed, and so on. Now right away let's take note of the fact that the value of this power series at x equals 0 is the leading coefficient c0. Now let's see what successive derivatives of this function look like and what their values at x equals 0 are. Differentiating term by term tells us that f prime of x equals c1 plus 2 times c2 times x plus 3c3 x squared, and so on. So we see that f prime of 0 is equal to c1. The second derivative, f double prime of x, is equal to 2c2 plus 3 times 2 times c3x plus 4 times 3 times c4 times x squared, and so on. So f double prime of 0 is equal to 2 times c2. Now, f triple prime of x is equal to 3 times 2 times c3 plus 4 times 3 times 2 times c4 times x plus 5 times 4 times 3 times c5 times x squared, and so on. And so we see that f triple prime at 0 is equal to 3 times 2 times c3. The fourth derivative is equal to 4 times 3 times 2 times c4 plus 5 times 4 times 3 times 2 times c5 times x to the first power, and so on. And so the fourth derivative evaluated at 0 is equal to 4 times 3 times 2 times c4. Now a clear pattern has emerged here. The kth derivative of f is equal to k factorial times c sub k plus k plus 1 factorial times c sub k plus 1 times x. And the kth derivative evaluated at 0 is equal to k factorial times c sub k. Now if we divide by k factorial, we obtain an expression for the kth coefficient c sub k. C sub k is equal to the kth derivative of f evaluated at 0 divided by k factorial. Note that this formula makes sense even when k is 0, provided that we interpret the 0th order derivative of f to simply be the function f itself. So, if f of x can be represented by a power series on the open interval from minus r to r, then that power series may be written as f of x equal to the sum from k equals 0 to infinity of the kth derivative of f evaluated at 0 divided by k factorial times x to the k, or f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed, and so on. This is the Taylor series of f centered at or about 0. This is also known as the Maclaurin series of f. This suggests the possibility of constructing a power series expansion or representation of any function f defined on an open interval centered at 0, for which the numbers f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and so on exist. In other words, for a function that's infinitely differentiable at x equals 0. Again, all that is required for the construction of a Maclaurin series, the sum from k equals 0 to infinity, of the kth derivative of f evaluated at 0 divided by k factorial times x to the k, is the existence of the numbers f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and so on. That is, the infinite differentiability of f at x equals 0. However, that is not sufficient to guarantee that the series converges to f of x anywhere other than 0. We will explore these issues in more detail in the next lecture. For now, we just state a simple theorem that will cover the most basic examples. Theorem: if there is a constant m such that the absolute value of the kth derivative of f is less than or equal to that m for all x in the open interval from minus r to r and all k greater than or equal to 0, then the Maclaurin series of f converges to f of x for all x in that open interval. Think of the hypothesis of this theorem as follows. If we were to graph f along with all of its derivatives over the interval from minus r to r, it would be possible to draw a horizontal line above all of those graphs as well as a horizontal line below all of those graphs. Example: Let f of x equal e to the x. Then f prime of x is equal to e to the x, f double prime of x is equal to e to the x, and so on. So f of 0 is equal to 1, f prime of 0 is equal to 1, f double prime of 0 is equal to 1, and so on. That is, the kth derivative of f evaluated at 0 is equal to 1 for all k. Therefore, the Maclaurin series of e to the x is the sum from k equals 0 to infinity of 1 over k factorial times x to the k, or 1 plus x plus 1/2 times x squared plus 1 over 3 factorial times x cubed, or 1/6 x cubed, and so on. The boundedness condition on f and its derivatives in the preceding theorem is true on the open interval from minus r to r for any r, with the upper bound capital M equal to e to the r. Therefore, the Maclaurin series converges to e to the x for all x. That is, e to the x is equal to the sum from k equals 0 to infinity of 1 over k factorial times x to the k for all x. Now let's note that replacing x with minus x gives the Maclaurin series for e to the minus x. E to the minus x equals the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x to the k, which is an alternating version of the series for e to the x. Another example. Let f of x equal sine x. Then f prime of x equals cosine x, f double prime of x equals minus sine x, f triple prime of x equals minus cosine x, the fourth derivative equals sine x again. And thereafter all derivatives cycle through the same four functions. So f of 0 is equal to 0, f prime of 0 equals cosine of 0, which is 1, f double prime of 0 equals 0, f triple prime of 0 equals minus 1, the fourth derivative at 0 is equal to 0, which tells us that any even-order derivative evaluated at 0 is 0, while any odd-order derivative evaluated at 0 equals either plus or minus 1, and in particular, the 2k plus 1 order derivative of f evaluated at 0 equals minus 1 to the k. Moreover, the boundedness condition on f and its derivatives in the preceding theorem is true on the interval from minus infinity to infinity with capital M equal to 1. Therefore, the following Maclaurin series converges to sine x for all x. Sine x is equal to the sum from k equals 0 to infinity of minus 1 to the k divided by 2k plus 1 factorial times x to the 2k plus 1. Notice that formula gives us only the odd-ordered terms, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial times x to the 7th, and so on. For the function cosine x, we would have found that all of the odd-order derivatives at 0 equal 0, while the even-order derivatives at 0 equal plus or minus 1. And so the following Maclaurin series converges to cosine x for all x. Cosine x equals the sum from k equals 0 to infinity of minus 1 to the k divided by 2k factorial times x to the 2k, which equals 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, and so on. Both of these are alternating series, except at x equals 0, and notice that the series for sine involves only odd powers, while the series for cosine x involves only even powers. This should not be surprising, since we know that sine x is an odd function, while cosine x is an even function. Now let's go back to the series for sine x. And notice that its partial sums are odd-degree polynomials in x. Let's plot the first several of those along with sine x and see how they compare. This is the graph of sine x along with the graph of y equals x, the first term in the series. This is nothing but the tangent line to the graph at x equals 0. Now when we add on the cubic term, we have the graph of the cubic polynomial that most closely fits the graph of y equals sine x near x equals 0. Adding the fifth degree term gives us an even better approximation near 0 and a fair approximation on a wider interval centered at 0. Now let's add the 7th degree term, and then the 9th degree term, then the 11th degree term, the 13th degree term, the 15th degree term, the 17th degree term, and finally the 19th degree term. This polynomial of degree 19 does a good job of approximating sine x over the interval from minus 2 pi to 2 pi. Now, if we add more and more terms, then that interval on which the polynomial approximates the sine function well will expand out and become as wide as we want. So in that way, the partial sums of the Maclaurin series will converge to sine x for any x. Example. We can find Maclaurin series for sinh x and cosh x by combining the Maclaurin series of e to the x and e to the minus x. Now recall that sinh x, by definition, is 1/2 of e to the x minus e to the minus x. Now using the series for e to the x and e to the minus x, this becomes 1/2 of the sum from k equals 0 to infinity of 1 over k factorial times x to the k minus the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x to the k. We can combine those two sums into one and write 1/2 of the sum from k equals 0 to infinity of 1 minus 1 to the k, all divided by k factorial times x to the k. Now that numerator, 1 minus 1 to the k, is equal to 0 if k is even and 2 if k is odd. This lets us rewrite the series as the sum from k equals 0 to infinity of 1 over 2k plus 1 factorial times x to the 2k plus 1, which is equal to x plus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5th, and so on. Notice that this is just like the series for sine x, except without the alternating signs. Now recall that cosh x is equal to 1/2 of e to the x plus e to the minus x. And so, in almost the same way as above, we have 1/2 of the sum from k equals 0 to infinity of 1 plus minus 1 to the k over k factorial times x to the k, and this time the numerator in the coefficient of x to the k is 0 when k is odd and 2 when k is even. So we can factor a 2 out of the series, getting rid of the 1/2 out front, and write the series as the sum from k equals 0 to infinity of 1 over 2k factorial times x to the 2k, which is 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, and so on. Now notice that this is just like the series for cosine x, again without the alternating sign. Now for reference, let's display our basic series for the functions e to the x, sine x, and cosine x, and let's consider the following example. Find a closed form of the power series x minus x cubed plus 1 over 2 factorial x to the 5th minus 1 over 3 factorial x to the 7th, and so on, which equals the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x to the 2k plus 1. To begin, let's notice that the denominator k factorial in that coefficient forces us to work with the series for e to the x. So we'd like to rewrite our series as the sum of 1 over k factorial times something to the kth power. We can accomplish that by first factoring x from the series, making the power of x in the kth term 2k, and then realizing that minus 1 to the k times x to the 2k is the kth power of minus x squared. So we have x times the series for e to the x with x replaced with minus x squared. And so the closed form of our power series is x times e to the minus x squared. Example. Find a closed form of the power series 3x squared minus 3 cubed over 3 factorial x to the 4th plus 3 to the 5th over 5 factorial x to the 6th, and so on, which equals the sum from k equals 0 to infinity of minus 1 to the k times 3 to the 2k plus 1 divided by 2k plus 1 factorial times x to the 2k plus 2. Now, the 2k plus 1 factorial in the denominator of the coefficient of x to the 2k plus 2 tells us that the answer is likely going to involve the sine function. So we'd like for the kth term to have the form of minus 1 to the k over 2k plus 1 factorial times something to the 2k plus 1 power. Since the power on the x is 2k plus 2, we need to factor x from the entire series, and once that's done, the kth term inside the sum becomes minus 1 to the k over 2k plus 1 factorial times the 2k plus 1 power of 3x. So we're looking at x times the series for sine x with x replaced with 3x. So the closed form of our series is x times the sine of 3x. Another example. Find a closed form of the power series 1 minus x squared plus 2 cubed over 4 factorial x to the fourth minus 2 to the fifth over 6 factorial x to the sixth, and so on. Now notice that we only have even powers of x, and the kth term appears to be minus 1 to the k times 2 to the 2k minus 1 divided by 2k factorial times x to the 2k. That formula works for all terms except the first one, the constant term 1. So let's write the series as 1 plus the sum from k equals 1 to infinity of minus 1 to the k times 2 to the 2k minus 1 divided by 2k factorial times x to the 2k. The kth term of that sum is clearly similar to the kth term of the series for cosine. So we'd like to rewrite that kth term as minus 1 to the k over 2k factorial times something to the 2k power. By factoring out 1/2, 2 to the 2k minus 1 power becomes 2 to the 2k power, and so our series becomes 1 plus 1/2 times the sum of minus 1 to the k over 2k factorial times the 2k power of 2x. Now notice that that sum is the series for cosine x with x replaced with 2x, except the k equals 0 term, or the constant term 1, is missing. So that sum is equal to cosine of 2x minus 1. So a closed form for our power series is 1 plus 1/2 of cosine of 2x minus 1. Now let's simplify this by observing that we have 1 plus 1/2 times minus 1, which equals 1/2, plus 1/2 of cosine 2x. We can factor 1/2 from both terms and get 1/2 of 1 plus cosine of 2x. And by a familiar trig identity, that's equal to cosine squared x. Taylor series centered at x0. Let f of x be defined by a power series about a given number x0 with a non-zero radius of convergence. In other words, f of x equals the sum from k equals 0 to infinity of c sub k times x minus x0 to the kth power, or c0 plus c1 x minus x0 plus c2 times x minus x0 squared, and so on. In the same way as before, we find that c sub k is equal to the kth derivative of f evaluated at x0 divided by k factorial. Therefore, the Taylor series expansion of f centered at x0 is f of x equals the sum from k equals 0 to infinity of the kth derivative of f evaluated at x0 divided by k factorial times x minus x0 to the kth power. A series constructed in this way will converge to f of x for absolute value of x minus x0 less than r if the absolute value of the kth derivative of f is less than or equal to a constant capital M for all absolute value of x minus x0 less than r and all k greater than or equal to 0. This statement is analogous to the theorem that we previously stated for Taylor series centered at 0. Example. Find the Taylor series expansion of sine x centered at pi over 4. First, let's list the function and its derivatives. Sine x, the first derivative is cosine x, second derivative is minus sine x, third derivative is minus cosine x, and by the time we get to the fourth derivative, we're back to sine x again. Next, we list the values of those at pi over 4. Root 2 over 2, root 2 over 2, minus root 2 over 2, minus root 2 over 2, then back to root 2 over 2 where we started. So all of those derivative values are either plus or minus root 2 over 2, and the sign cycles through plus plus, minus minus, plus plus, minus minus, and so on. So we can factor root 2 over 2 from the entire series and write sine x equals root 2 over 2 times 1 plus x minus pi over 4 to the first power minus 1 over 2 factorial times x minus pi over 4 squared minus 1 over 3 factorial times x minus pi over 4 cubed, and so on. Now let's see how we can express this using summation notation. The signs of the terms don't strictly alternate, but alternate in pairs, plus plus, minus minus, plus plus, and so on. We can represent that sign pattern using the floor or greatest integer function. We'll write this series as root 2 over 2 times the sum from k equals 0 to infinity of minus 1 raised to the greatest integer in k divided by 2, all divided by k factorial, times x minus pi over 4 to the k. Now let's think about the minus 1 raised to the greatest integer in k over 2. When k is 0, the exponent is the greatest integer in 0, which is 0, and so we have minus 1 to the 0, which is 1. When k is 1, the exponent is the greatest integer in 1/2, which is again 0, and so again we get minus 1 to the 0 power, which is plus 1. But when k is 2, the exponent is the greatest integer in 1, which is 1, and so we have minus 1 to the first power, or minus 1. When k is 3, the exponent is the greatest integer in 3/2, which is again 1, and so again we get minus 1 to the first power. Now when k is 4, the exponent is the greatest integer in 2, which is 2, and so we have minus 1 squared equals plus 1. And when k is 5, the exponent is the greatest integer in 5/2, which is again 2, and so we again get plus 1. In general, when k is a multiple of 4, or one more than a multiple of 4, the greatest integer in k over 2 will be an even number, and so minus 1 to that power will be plus 1. Otherwise, the greatest integer in k over 2 will be an odd number, and minus 1 to that power will be minus 1. And so this does in fact give us the sign pattern that we want, plus plus, minus minus, plus plus, and so on. Now let's think for a minute about why we might want to have a Taylor series expansion of sine x centered at pi over 4 rather than 0. The partial sums of the Taylor series can be used to approximate values of the function on an interval centered at the choice of x0. And generally speaking, it's best to choose x0 to be the center of the interval on which you want the approximation. And you'd also like for the interval to be as small as possible in order that a good approximation can be obtained with as few as possible terms of the series. Now, in the case of the sine function, all of its values on the entire real number line are plus or minus a value that occurs between 0 and pi over 2. And so if we can accurately compute values on that interval, we can transfer those values, or their negatives, anywhere we want them to be. For instance, on the interval from pi over 2 to pi, sine of x is equal to the sine of pi minus x, which is between 0 and pi over 2. On the interval from minus pi over 2 to 0, sine of x is equal to minus the sine of minus x, and minus x would be between 0 and pi over 2. And on the interval from minus pi to minus pi over 2, sine of x is equal to minus the sine of x plus pi, and x plus pi is between 0 and pi over 2. And similarly, the values of the sine function between 0 and pi over 2 can be transferred to any place on the real line. Now let's compare, on the interval from 0 to pi over 2, the cubic approximation obtained from the Taylor series centered at pi over 4 with the cubic approximation obtained from the Maclaurin series, or the Taylor series centered at 0. Notice that the cubic approximation centered at pi over 4 does a pretty good job of approximating sine x over the interval from 0 to pi over 2, while the cubic approximation centered at 0 does not do very well near pi over 2. However, it does do a better job on the other side of 0. These pictures illustrate the fact that if we want to approximate sine x on the interval from 0 to pi over 2, we would need to use higher degree terms from the Taylor series expansion about 0 than we would from the Taylor series expansion about pi over 4 in order to obtain the same accuracy. One more example. Find the Taylor series expansion of the square root of x centered at 1. Here it should be clear that since the square root of x is not differentiable at 0, a Taylor series expansion about 0 would be impossible. So first let's list the function and its derivatives. The square root of x, 1/2 times x to the minus 1/2, minus 1/4 times x to the minus 3/2, 3/8 times x to the minus 5/2, minus 5 times 3 divided by 2 to the 4th power times x to the minus 7/2, 7 times 5 times 3 divided by 2 to the 5th times x to the minus 9/2, and so on. The values of those at 1 are 1, 1/2, minus 1/4, 3/8, minus 5 times 3 divided by 2 to the fourth, 7 times 5 times 3 divided by 2 to the fifth, and so on. Now we'd like to write down a formula here for the kth term. First, notice that with the exception of the first term, the terms alternate in sign, with the kth term positive when k is odd and negative when k is even. So our formula will involve minus 1 to the k minus 1, beginning with k equal to 1. Also notice that the denominator of each fraction is simply 2 to the kth power. The numerators, beginning with the k equals 2 term, which is minus 1/4, are similar to factorials. Each one is an odd positive integer times all of the odd positive integers down to 3 times 1. A product such as this, that is, the product of some positive integer times every other positive integer down to either 2 or 1, is called a double factorial. In this case, the greatest number in that product in the kth term turns out to be 2k minus 3. And so we can write the kth term for k greater than or equal to 2 as minus 1 to the k minus 1 power times 2k minus 3 double factorial divided by 2 to the k. So the Taylor series is 1 plus 1/2 times x minus 1 plus the sum from k equals 2 to infinity of minus 1 to the k minus 1 times 2k minus 3 double factorial divided by 2 to the k times k factorial times x minus 1 to the kth power. The first several terms here are 1 plus 1/2 times x minus 1 minus 1/8 times x minus 1 squared plus 1/16 times x minus 1 cubed minus 5 over 128 times x minus 1 to the fourth. The radius of convergence of this series turns out to be 1, as we should expect it to be since the square root function is not differentiable at 0. Here's the graph of the square root function along with the degree 10 approximation centered at 1. Notice how the graph of the polynomial here quickly diverges away from the graph of the square root function outside of the interval from 0 to 2.